Chapter 17, Equilibrium. We're only going to talk about highlights of this chapter as well. One thing that's important to talk about is a collision model, which helps us to explain how chemical reactions occur. And according to collision model, molecules must actually collide. They must meet, right, in order for a reaction to occur. And we can kind of think of this in terms of people as well, where a reaction would be maybe some romantic interest between two people. In order for you to be interested in someone, you have to know they exist and meet them in some way. You know, since there's been online dating and stuff, people claim to fall in love without actually having met the other person, but we'll ignore that. You need to meet the person. So in order for molecules to react, they need to collide. They need to run into each other. And how fast they collide is going to depend on the concentrations of the reactants and on the temperature of the substance. So here we have an illustration of two bromine, let's see, I don't know if that'd be hyponitrite. We'll just call it BRNO. BRNO molecules colliding. They're going to approach each other at high speeds. A collision occurs, and then as a result of the energy from the collision, existing bonds are broken, which makes way for new bonds to form. These atoms here are covalently bonded to each other. It's a pretty strong force holding those atoms together. And in order for them to react and form a new molecule, we have to break the bonds that are existing. Let's see, where's this going? Concentration will increase the rate of a reaction, how fast the reaction occurs, because it leads to more collisions. So think about a room full of people, and maybe a room this size without all the chairs, and there's 5 people, and they're walking around. Are they going to bump into each other very often? No. What if you had 100 people in this room? There will be a lot of bumping, right? Running into each other just because it's crowded. So that's how concentration works with chemical reactions. The higher the concentration of your reactants, the more collisions occur. Temperature will also increase the rate of the reaction. And this little diagram helps us to understand why. At a higher temperature, the particles have higher kinetic energy, which means they move faster. Remember, we talked about barefoot people on the beach. Hot sand, people are moving faster. Hot molecules, they move faster. If the particles are moving faster, imagine the 5 people running in this small room. They're going to run into each other more often? Yes, just because of their increased speed. But not only more collisions, but more high energy collisions. You can have a collision between 2 molecules where nothing happens because there's not enough energy in the collision to break the existing bonds. Just like I think we've all heard stories of people who eventually fell in love and got married, and like 5 years before they got involved with each other, they had this random meeting but nothing happened because they weren't in the right frame of mind or whatever, but they had this chance meeting and nothing happened. That can happen with molecules too. They can be moving so slowly they bump into each other and they go, and they go off and nothing happens. But if they collide with enough force, then a reaction occurs. So with more high energy collisions, we have more of those collisions that actually break the existing bonds, and so we have a faster reaction. So increasing the temperature usually increases the rate of a reaction. Increasing the concentration usually increases the rate of a reaction. Activation energy is an important concept. Chemists, scientists in general, we like diagrams because it helps us to visualize things that are very hard to visualize. So here, again, we're talking about the same reaction. Here's our reactant, BRNO, and in order for those 2 particles, 2 molecules to react, they have to collide with a certain amount of energy. This is called the activation energy. And personally, I think this looks like the side view of a miniature golf course. And there's those darn little humps, right, on the greens. And so here you are, and you're gonna. That's your putter. You're frustrated and waving it around. And here's your ball. And so you need to hit the ball and get it up over this hump. What happens if you don't hit it hard enough? It goes part way up and it rolls back down, and you have to do it again. So in order for your ball to go over the hump, you have to give it a minimum amount of energy to get over. If you hit it harder, it will still go over, right? So in order for these molecules to collide, this is the amount of energy that they have to have when they collide. It's called the activation energy. It's the energy required to break the existing bonds. When those bonds are broken, the new bonds can form. Once you get over that hump, it's downhill. And the reaction precedes it all because the products are going to be at a lower energy than the initial reactants. We know that things don't roll up hills, right? They roll down. And so when we talk about an energy diagram, we can kind of visualize that this is involving going up. The only way it goes up is if something puts energy into it. But once you get up over here, it'll just happen by itself. It'll roll down by itself. And so a chemical reaction occurring generally requires some kind of investment of energy. Just like in the financial world, it's hard to make any money if you don't have at least a little bit of capital to invest in something. You know, you can't make money in the real estate market if you don't have enough money to buy some real estate in the first place. And so you need to invest some energy, and then you get a payback of greater energy. Question?
So the catalyzer would be something that would lower the energy requirement?
Exactly.
Like make the
Yes, exactly. So he says the catalyst would make the activation energy lower, the hill lower. Yep. There we go, right here. I didn't arrange that beforehand. He came up with that himself. So what does a catalyst do? A catalyst provides an alternate pathway that is lower in energy so that these molecules can react with less investment of energy. So if you're playing miniature golf, it's going to be shaving the top off that hill. So now when you're hitting the ball, trying to get it over, it's going to go over more often because it doesn't require as much energy. A catalyst is something that will speed up the reaction without being consumed by the reaction. So it's not a reactant. So the miniature golf analogy doesn't work as well here. Let's think about, okay, so here's a bunch of kindergartners. I really have no idea where these analogies came from. They pop into my brain. So for some reason, these kindergartners need to get to the other side of the fence. One of these years I'll come up with a reason and make this even more colorful. But the kindergartners need to get to the other side of the fence. So this fence is like an activation energy. They have to climb up and over the fence, and that is slowing things down, right? If there was no fence here, they would just run to the other side and be fine. So a catalyst can work in a couple of different ways. One example of a catalyst would be, let's bring the teacher out here. And as these children approach the fence, it takes them a while to climb over. The teacher's just going to pick them up and lift them over the fence. And so they're going to get over more quickly. The teacher is there and can cause a lot of students to go over the fence. She doesn't go over the fence with the students. She does not get used up. So one at a time, she lifts them over the fence. Now there's, a certain rate at which a catalyst can catalyze a reaction, but it's very important to understand that a catalyst is not consumed. Enzymes are biological catalysts. Your body is full of them, and you need them. And they work by providing a new pathway with a lower activation energy. So these children going over the fence, the teacher is providing a lower energy pathway because it's a lot less energy for these students to be lifted over the fence. Another way we could cause a lower pathway is to take out part of this fence, right? If we took out the top 2 rails of this fence and just had this lower one, now it's going to be a lot easier for those kindergarten students to hop over the fence. And that's another way of thinking about a catalyst. Any questions? Equilibrium. Okay, so now we're finally getting to the subject of the chapter, right? All that other stuff there. So equilibrium. What do we think of when we hear the word equilibrium just in everyday life? Balance, right? And it's stable, you're not falling over to one side or another. If we say, oh, I've lost my equilibrium, it means things are off kilter in my life, right? So equilibrium is a balancing. It's the balancing of 2 processes that are opposing each other. So one process is the opposite of the other. And a good example of this is evaporation and condensation. Evaporation is particles going from the liquid state into the gas state. Condensation is the opposite, going from the gas state into the liquid state. At equilibrium, these processes are exactly balanced. The rate of one is equal to the rate of the other. They're just going in opposite directions. Chemical equilibria are dynamic states. So it's dynamic. When we look at it on the surface, it doesn't appear that anything's happening, but actually a lot of stuff is happening. So let's look at this example. So here we put this liquid in a flask and we stopper it. And this picture is where we've just put the liquid in there. And the liquid will begin to evaporate. So particles will move from the liquid state into the gas state, and there will be a specific rate at which the evaporation occurs. At this point, there is basically no condensation because there's really no molecules in the gas state, so you can't have any condensation. So here the rate of condensation is almost 0. As this proceeds, we have evaporation continuing. We get more and more particles in the gas state, and now we have some condensation occurring. So the rate of evaporation is constant. The rate of condensation is increasing because the concentration of these particles in the gas state is increasing. Remember, we said that the rate of a reaction depends on the concentration. Well, this doesn't really work with collision theory, but the idea is the same. The more particles you have in the gas state, the faster they will condense. These particles, like all gases, are just zipping around. Eventually they're going to hit the surface of the water and get stuck. So at equilibrium, what we have is we have a balance between the process of evaporation and the process of condensation. And so the number of particles in the gas state is the same. And the level of the liquid is the same. But the particles are constantly changing. It's a little bit like a busy airport. So I don't know, like LAX. If you looked at LAX during the peak portions of the day, the number of people in the terminal would probably be relatively constant. There wouldn't be huge fluctuations. But you've got airplanes coming and people getting off and coming into the terminal. You also have airplanes leaving and taking people out of the terminal. You have people coming from their cars and people going to their cars. So is it the same people in the airport all day long? No. Can it be the same number of people? Yes. If the number of people arriving is equal to the number of people departing, the number of people in the airport doesn't change, even though the individual people are different all the time. And so that's what's going on with this equilibrium between evaporation and condensation. The individual, think of this as the airport. The people, the molecules in the gas state are constantly changing because they're entering the gas state and they're leaving the gas state. But overall, the number of particles there is the same. So it's balanced, it's an equilibrium, but it's dynamic because things are changing. So when we look at a chemical equilibrium, if we look on the molecular level, what are the molecules doing or what are the atoms doing? There is frantic activity. There is a lot going on, right? Equilibrium is not static. It's not frozen, right? But it's dynamic. Macroscopically, that's what we can see with our eyes. Without using a microscope or anything, just what you can see. Macroscopically, it is static. It looks like nothing's happening. But microscopically, or on the particulate molecular level, it is very dynamic, and there's a lot going on. Any questions? Here's a more detailed diagram. Here we're looking at a reaction between, we've got the reaction of water and carbon monoxide to form carbon dioxide. So initially in this container, it says we have equal numbers of moles of water and carbon dioxide. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. So we've got 7 of each. The reaction begins to occur. And so here's a molecule of CO2, here's a molecule of hydrogen. So the reaction is beginning to occur. We really need to write this out here. So here we have, don't write with the eraser, it doesn't work very well. We have H2O plus carbon monoxide, and that's forming CO2 and H2. This is an equilibrium, and so we usually use a double-headed arrow to show that the reaction goes in the forward direction, that water and carbon monoxide will react to form these two, but these two molecules, carbon dioxide and hydrogen, can also react to form the original reactants again. So the reaction can go in both ways. So here we're seeing the forward reaction beginning to occur. These hydrogen molecules and carbon dioxide molecules just formed. They haven't had a chance to react in the reverse direction yet. As the reaction continues and more of those particles, more of these products are formed, now the reverse reaction is going to happen at a faster rate. And eventually we're going to get to this state of equilibrium. Time continues to pass, but the number of reactant and product molecules are the same. We don't see any more changes. And yet the forward reaction is occurring and the reverse reaction is occurring. I suppose you could think of it too a little bit like maybe your checking account. And money comes in, but money goes out. It always seems to be right at that just scary level, right? You're like, oh man, I'm just on the edge. And yeah, paycheck comes in, but then the mortgage is due. And so it comes in and it goes out, and yet if you look at your balance from month to month to month, a lot of times it's very much the same. That's a little bit what an equilibrium is like. Was there no money moving? No, there's a lot of money moving. A lot of people have huge turnover in their personal finances, thousands of dollars a month. And yet from month to month to month, the average balance remains the same. I don't know if that helps. If we look at at a graph of the rate of this reaction, so here the blue line is the rate of the forward reaction. So initially, all we had was water and carbon monoxide. And so the rate of the forward reaction was very high because the concentration of those reactants was high. And the pink line is the rate of the reverse reaction. Initially, it was 0 because the reverse reaction involves hydrogen and carbon dioxide, and there wasn't any. Because all we put into that jar was water and carbon monoxide. As the carbon monoxide and the water begin to react, the concentration of the reactants begins to decrease, and so the rate decreases. As this forward reaction occurs, the concentration of the products, which are the reactants for the reverse reaction, that's just a lot of confusing words, isn't it? The rate of the reverse reaction increases. And so we see the rate of the reverse reaction increase. And this will keep increasing, and this will keep decreasing until they meet somewhere in the middle. And at that point, they will remain in equilibrium unless something disturbs them. Because the concentrations of reactants and products will be the same. So the rates of the forward and reverse reactions will be the same. There's a lot of stuff going on, but the net effect is nothing, no change. So in a chemical equilibrium, concentrations reach levels where the rate of the forward reaction is equal to the rate of the reverse reaction. So consider an equilibrium mixture in a closed vessel. This is that same reaction that we were looking at. And let's say we add some water vapor to the flask. How does the concentration of each chemical compare to its original concentration after the equilibrium is reestablished? So we have an equilibrium, and these have gotten into balance so that the concentration of each of these is not changing. What happens if we add more water? Does that affect the rate of the reverse reaction? Why would it affect the rate of the reverse reaction? These aren't changing yet. If we add water, we're going to affect the rate of the forward reaction. Because if we increase one of these concentrations, the forward reaction will go a little faster. And so that will cause the concentrations of the products to go up a little, which will cause the reverse reaction to increase. And it'll go back and forth like that until it settles on a new equilibrium. This is a question that's really a little too high for this class, so we're not going to mess with it too much. This is for next week.